Greeting guys. It's actually another short sharing that I would love to actually share to all my subscribers and those who are new to my channel. Welcome. My name is Rishal and I hope my current sharing is going to be benefit and also it's going to be fruitful for everyone in the IC design career. One thing is that I just wanted to actually have this sharing, and it may actually you have known this earlier or before this as well. And here I am to do a short sharing. How are you actually going to answer a few questions in the interview, or perhaps in the work area, or even you might actually pondering what is it about. So let's do it in a small, in a different way. Sometimes your interviewer might actually ask you, what is the biggest problem that you have actually faced in your physical design and how do you solve it? Sometimes this is actually a open question to you. It's some sort of like a subjective and you really need to answer to it rather than giving you a direct technical question. Sometimes people will actually be thinking what you have actually done. You might actually have lost. So that's the reason before you really lost into something, you really need to understand what is the problem statement in IC design. What is the root that you are solving and then you taping on. So basically, I would love to actually say it PPA. P, we actually stand for power, performance, and then area. So the moment you really understand what is power, what is performance, and what is area, immediately you'll be thinking, oh yeah, I actually fix this because I have a power problem. I fix this because of the performance problem. Whenever you're talking about power, it's because there are high power dissipation in your design and you wanted to meet the criteria of the power. Probably due to that, you might actually fix your CPS. It's because while your power have increased due to switching factor, because you have a lot of cell being added during that period of time, that's the reason you having a power consumption increased. When it comes to performance, timing, you might actually have a criticalness. You might actually unable to fix your whole violation or perhaps setup violation. You might actually have a high frequency design and you fix it accordingly. You try to fix it and then you can actually propagate that to your interviewer. Last but not least, on area. Mostly on area part, mostly on the congestion. Your floor plan. You might actually tell you were given a small floor plan or an amount which unable to actually cater all your standard cell and also your macro blocks. You might actually have problems over that. So you really need to figure out how are you actually going to explain to your interviewer. So here it is. Maybe I give you a short example how you or me gonna actually answer to it. Trust me, even I've screwed up a lot of things, but this sharing gonna benefit you to the most. Perhaps I make one sharing where you might actually find it problems during your floor plan. Let's say this is an area issue. So immediately you will talk about area issue over here. So let's say this is your whole top floor plan and then you are trying to actually make connection of the interface, but then you are actually failing to do so. So the thing is that you might actually have like it's an amount of X and amount of Y. Out of X, 90% of them are actually used by the macro blocks. Let's say this much being used of the macro blocks, and then X, 90% of it are used by macro block as well. So you have an amount of X over here. It means that you might actually see a problems over here why it actually having a congestion over there. You might actually see congestion one thing. You might actually see mainly either routing congestion, or you might see cell congestion over here. So how do you fix it, and why you are actually having congestion? Maybe you might actually be having a lot of ports over here. If let's say every port's being aligned with one layer, then should be fine. If let's say you are stacking another port on top of them, what would happen? You would definitely see congestion, routing congestion over that particular area. And how do you actually fix it? You can actually make a routing blockage, or if there is a cell congestion, you can make a placement blockage over there. But at the same time, you have to really check it out whether those net that actually being connected to the rest are actually doing good. Probably, maybe the arrangement might be actually wrong. You can actually tell them, how do you actually identify the arrangement of the port? How do you actually fix the congestion over there? Why are you actually stacking up two metal layers over there? Maybe you can actually tell them you were given a small an amount of area, and that goes, you actually manage to fix it where you can actually stack two layers of ports over there. So this is how you can create, or you can share how you are actually explaining to the interviewer by actually explaining certain things on this part. There are more things you can actually explain. It's not only this. There might be some other issues where you can relate. If let's say you are having a power drop issues, how do you actually fix the power drop? Is it an amount of power being supplied over here? Do you think it's sufficient? And how do you fix it if it is not sufficient? So you can actually talk about that. So as usual for me, I always put myself into an area where you need to understand PPA first for the problems, and then you try to dissect it one by one. For instance, if you look the analysis as well, you can actually figure out what to do and not to do. First, you need to understand how to fix your hold and setup violation. Immediately you can actually think, did I actually have any issues back then? And then you fix your max cap, trans, and fan out. You can actually figure out on this what you have actually fixed, your cap, trans, and fan out. It's the design rule. You actually violating the design rule. What makes it got violated? You can actually understand that. And that's the reason this could actually lead into floor plan. Easily you can actually tell them, I actually solved this thing, and making sure that it actually meet the requirement over here. And then you can actually talk about IR drop, which is the voltage drop. Sometimes in certain area, because of too much of cell congested over that particular area, you wanted to actually spread it out over there to make sure you fix your IR drop over there. You have to actually know about this. It'll be easily for you to really relate. Just point it out, whatever analysis, point it out area. Immediately you can actually know. You pointed out PPA. From there you pointed out analysis. Then you pointed out whatever I've actually mentioned it over here. And then you can actually talk about crosstalk. In crosstalk, there are two types of crosstalk. One, we can talk about delay crosstalk. Another one more, we can talk about delay is the timing. Another one more is the signal crosstalk. Sometimes, because of the nets that actually moving very fast, that makes your victim net move faster as well. This is actually related to your CDS. And then there are some net that is actually ideal, that makes the aggressor who are actually having 0 or 1, that makes the victim net to change the value and may cause your design to be failed. You can actually talk about that. Then after that, you can actually talk about your antenna issue. So this antenna issue pretty much might not be the issue, because it's either you can actually jog it or add a diode. There's nothing much for you to actually say it out over here, but immediately you can just say we can actually jog it, or you can actually add diode to it to fix your antenna violation. Immediately you know, oh, okay, that's good. It's whenever you have an open-ended question, try to actually build a situation. You have to build a situation in order for you to actually think, how are you going to solve it? How going to do it? And then the next one is on DRC and LVS. So you really need to understand, did I actually miss anything over here? 1, 2, 3, 4, 5, 6, 7. I think I missed something, which is EM, electromigration. Yeah, I missed this thing. So coming back to here, I'm sorry guys. So coming back to here on the DRC part, every single stage, whenever you are in floor plan, whenever you are in CDS, whenever you are in routing, floor plan, placement, CDS and routing, even in ECO, you really need to take care of your DRC. Why your DRC values increasing as flows goes on? You really have to understand that. Why? And then how do you actually fix it? Sometimes the congestion causes DRC issue. If you solve congestion, your DRC issue will be gone. And then your LVS, your layout versus schematic, making sure it is correctly being connected according to your physical and also your schematic. It's like you are versus your functionality and also your physical layout. But last but not least is electromigration. It's all about the reliability. I think if you really fix these crosstalks, IR drop, immediately it can actually fix your EM, even your transmax cap. So pretty much you build a situation where you tell to the interviewer, hey, I came across to this and this and this. That's all. Pretty much you have to build a situation. Probably you draw a layout. From the layout itself, you try to dissect smaller and smaller and smaller, making sure you understand how it is being solved during that period of time. So I really hope you really enjoyed my video so far. So coming back to summarize the whole part over here, you really need to understand the PPA. PPA is the ultimate goal. This is actually your ultimate goal that you really need to understand. If you really understand the ultimate goal, immediately you'll move on into analysis. I actually have a better idea for you guys to really think, how are you going to explain this, whether in the interview or perhaps in your career, or for you to actually have a critical mindset. Immediately you can actually tackle any issues that you are facing in the physical design. First, you need to understand the flow very well. The flow, what I'm trying to say here is, regardless wherever you are in the IC design part, you really need to understand the whole flow. Whether it is architecture, RTL, synthesis, PNR. Once you finish your PNR, immediately it's actually tape out. I mean, of course, you have to clean up all your base layer, then checking out everything, sign off, clear, foundry. Then after the foundry, you bring it over to packaging. After packaging, to your testing. So how do you interrelate the stakeholders? Perhaps that actually comes into a macro level. But here the micro level is for you to answer. It should be on the analysis part, the most important thing. That's why we go into analysis. Once you know the analysis, you immediately know your issues. Once you know the issues, once you really understand the issues over here, immediately you would actually able to understand how do you actually solve it. Hold on. The moment you solve it, it's not something like, you are actually relieved. It's not something like that. Whenever you actually do the solving part, you really need to understand how to verify it and validate it. You have to make sure that's the reason it goes like a flow chart. Then it moves down all over again until you make sure that it is clean and it's giving a green signal. It means you are good to go. So coming back here again. whenever you really wanted to answer, try to bring it over the analysis that you actually done. Open up your floor plan that you actually have done before. Immediately, you can actually trigger what you have done in the past. The problem that I had in the past is because whenever a question is thrown, you try to actually think what you have solved rather than thinking what was the main goal. From the main goal, how do you dissect all the way to bottom? So you really need to make sure that, furthermore, if, let's say, you understand the whole concept of P&R flow, this will not be a problem for you anymore. It's like some sort like you are opening a book and you are summarizing the whole thing to the interviewer. That's the best thing. On top of that, maybe I've not covered one part which is on the low power. So how do we actually talk about low power part? So let me I hope you guys have actually understand how these whole pictures actually come from. There are more things you can actually explain, but more or less it is actually being explained, except the timing part, which I may not actually touch. But as usual, when it comes to timing, you have to make sure you actually fix it your hole and also your setup. And on top of that, it depends on your timing guideband. How do you actually fix it? That's why we actually have this AOCV, POCV and OCV, how these things actually embed with your timing issues. So that's something that you can actually talk about if you have some problems. So, but I would love to actually try to relate more on low power. I'm trying to make this video more interesting in different areas. So let's move on into low power part. So immediately, when you talk about low power, just for your information, this is more exactly targeting only on physical design. Let's not talk about the RTL part or architecture part. Perhaps, maybe on some other videos, maybe we can actually counter that or tackle that more intensely soon. So low power, definitely when you talk about low power, is always about UPF. You need to understand what is the content inside UPF. From there on, you really know the bigger picture of what is low power about. Let me give you a small brief idea about UPF. In UPF, there's only 6 segments. Main on the 3 parts of the whole macro area, 3 parts of the micro area. So normally this is how I actually tackle my issues, to get to know what is the macro area part and also what, on the other hand, what is the micro area part. So on the macro area part, you really need to understand about create power domain, and then your power state table, and then your system interface connection. Why power domain is important? Because when you create your floor plan, there will be island being created. There will be different power domain will be created based on the power, that based on the voltage or domain that actually being assigned to make sure it is a low power. If you know where it is being located, at the same time, hierarchy plays a biggest role over here. If you do not understand the hierarchy, where is the power domain located, then you might not able to actually see it, where is the problems come from. And then power state table is like a map. It's a map to your floor plan. If you do not know how to read your power state table, then you might actually encounter a lot of problems. You probably might actually able to see it, which area is actually off, which area is on, and sometimes it actually goes independently as well. Why I'm saying independently, it's because sometimes one domain switch off, another few more domains is on, but the other domain switch off, it might not be actually this domain are actually on or off. So you really need to understand the scenario given in power state table sometimes can be varies. So that is the reason you have to pay attention to the details of this power state table to make sure that you really know what the issue is going to be in the future. And then when we talk about system interface is on the what are those pots that being actually defined by you. So you really need to understand that. You really need to know what are you actually defining. on the power, sometimes the RTLer or perhaps the UPF owner might actually mistake the definition. They might actually define incorrectly. That can actually cause you MV violation. That's the reason you have to check your SRSN to make sure that you really know your system interface is actually being defined correctly. On the other hand, this is actually a backbone. The implementation comes here is on the isolation, level shifter, and your retention cell. So you really need to understand that why isolation being inserted. And isolation is being inserted when you are actually having a gated to ungated region, because the gated region is actually turned off, and then there is a signal being propagated while the domain is actually turned off. It makes unknown value. Whenever it is an unknown value, it could cause a failure to the design. And whenever there is a failure to design, you definitely eventually cannot actually power on your design. So that's the only reason. So the problem here is that you really need to make sure to have a deterministic value on each and every single part of your design. I'm clear on one. So on the level shifter, you actually might have a different voltage across your design. You might actually go from high to low or low to high. Let's come in talk about the level shifter. So about the level shifter over here, as I mentioned earlier, if it is a high to low, it's okay. It's because you are not actually going to change the value, but you don't want to stress your transistor, so that is the reason you are actually adding a level shifter. But whenever it actually propagating from low to high, that's where you actually gonna have a lot of issues over here. Whenever you are having a lot of issues over here, then there will be a failure in your functionality, because whenever it actually propagating 1 or 0, you might not actually seeing it in the high 1 or 0. So that's the reason you need to add your level shifter in order for your low power design to actually work. So this is the whole concept that you really need to understand. This is just a simple concept that I really wanted to actually explain, which I'm going to actually show it to you right now on the following. So let me just draw a simple diagram just for you guys to really understand. Just give me a moment. So let's come back here again. So maybe we are actually having a gated region over here. We have a gated region over here, and then we have an ungated region over here. Okay, so over here, what we could actually see is the issues here is on the fixed max trans on this part. You might actually be thinking, hey, if it is actually defined correctly, why the tools is actually not adding the correct cell to solve the trans issue? So over here, you have to understand, we actually see ISO cell, we actually see level shifter cell, we actually see a retention cell. But I forgot to actually mention one more cell. It may not be as functional as it is, but it is a functional cell, which is always on cell. This is actually a buffer. You really need to understand this. This is actually a buffer. You have to make sure that you understand the whole concept, how low power being implemented. So again, coming back here, without any further ado, let's come back here and let me actually explain to you. So whenever we talk about this gated region, it means that this area, whenever it is turned off, the signal that propagating from here, X, to outside Y, would be X, and it will be unknown. So we don't want that to happen. To ensure you have a deterministic value, you need to either add your isolation cells inside the design. So here it is why actually we're going to have a trans issues over here. Let me explain in quite a while. So let's say you are having an AND gate over here. You're going up, and then you might actually have an inverter is actually going up, and then you actually having a a PMU over here, power management unit, and then it is actually driving 0, then one inverter will be added, and then another one more. So whenever it's 0 here, it 1 here, and then here 0 is propagated. So here it is, isolation cell is being added either OR gate or AND gate. It's either these two gates. It's because we want to make sure that we want to have 0 or 1. I think everyone knows whenever it comes to digital logics, we have to know, hey, I wanted to see 0 or 1. Obviously, whenever you actually see the rail timing, it does not give a perfect value of 0 or 1. There will be like a bit of jitter over there. So some sort, I mean, that's a part of that. Let's not talk about that. So just come back to here. So you really want either 0 or 1. So in order to do that, you want to, if you look up on LUT, on the lookup table, if it is an OR, any value against 1, you will result as 1. If it is an OR, and AND, any value that is actually giving 0, it would actually give 0. Even if you were actually giving 1, the odd, whether it's 0 or 1, you will actually, if it is a 1, it would actually 1. If it is 0, it would actually 0. So to make it simpler, you really want to make sure you have an output of 1, immediately you're going to add in an OR gate. If you really want to have an output of 0, immediately you add an AND gate, because and a 0 is over there, immediately your result is going to be 0. So outside world, you have an OR gate over here, and then maybe an AND gate over here. So the thing is that 1 over here. So right now we want to add either, so there will be another signal will be connecting to here, and then another signal coming from here be connecting here. So right now, you have to remember, isolation cell is the bridge between your gated and also ungated. So you have to add your isolation cell in between of these two cells, which is over this area, X and Y over here. So I'm going to actually make it this guy as to make sure an OR gate. So here it is an OR gate. 1 will be connected over here and will be labeled as X, and then we connect this OR gate to a 1 here, and then we connect this AND gate. We connect an AND gate over here, and then we connect this guy over here, and then this connect to here. So it means that, and this guy connect to here. It means that this is X and this is 0. This is X, this is 1. Immediately you will get a value of 1 over here, and immediately you will get a value 0 over here. There you go. You already have a simple connection of isolation cell. But here it is. What is the issue that you might actually see in a low power? Normally, in a low power issues, there are actually more. But then, I'm just giving you an example. You might actually see a transition value. Why you might actually see a transition value is because you would be actually putting these guys somewhere very close to the next cell inside ungated. And you have a long domain over here. So you have to actually add one buffer over here, or even perhaps you would add buffer around this area, but somehow it is actually two different domains. So whenever it is two different domains, you need to understand that you need to actually add a always on buffer over there. So maybe I put it a big one over here, either here or here. So you need to have two types of power rail that is actually connected to here, or you can actually connect it to outside or weight. So whichever area that you see the problem, you add over there to make sure that you satisfy your multi-voltage issue. This is considered as multi-voltage issue. At the same time, you have to make sure that you have a better place of your SRSN port as well, your power switch. So this is something that very simple idea. And then how do you actually solve it? Sometimes tools are unable to actually add it because it might get actually confused. Hey, what kind of, maybe it may actually add a wrong cell over there, and it might not define as as a proper always on cell. So the tools might not be intelligent enough, they might actually miss out. So this is actually another issue that you might actually see. So here it is, let me summarize. I have actually explained the whole part over here is on the analysis part. We want to see what kind of analysis part that we are missing here. I think one part is IR drop and power dissipation issue. Yeah, I think maybe during CTS you might actually see a lot of issues seeing power dissipation. So you might actually want to change it into either into a HVT cell that actually have a lower leakage. I think let's not talk about that because I actually missed out one part. That's the reason I'm actually adding this. So the main point here is you need to know what is the ultimate goal that you are actually achieving at the beginning itself. Regardless of any design, you immediately you will get to know the main idea. How do you actually see it? How do you actually fix it? So first, get to know your PPA. What is PPA about? Once you know your PPA, go back to your flow. Which are the flow that you are having issues, and then straight that dissect it. What kind of analysis that you wanted to actually have it over there. Immediately, you would definitely understand, oh yeah, I have this issue. I solved this. I have that issue. I solved that. You try to make yourself be more comfortable whenever you try to actually answer any. It's okay, take your time. Sometimes it may actually dragging a bit, but be precise and get to the details as soon as possible. But if you really have the capability, immediately straight, hey, I have this floor plan, I have this problem, immediately straight go into the details, then it's good. But here, why I'm telling you this, for those people might actually have a lot of things to do. Like for instance, there are people who are actually try to work it on architecture, work it on RTL, work it on synthesis. They might not actually able to really put a lot of priority. Hey, I have this concrete issue that I need to solve that. Did you get it over there? Because the whole point here, if you have a very good data flow, if you know the architecture properly and you know your data flow is working this and this immediately, and you roughly know about the distance, there you go, you don't have any issues. But there are people who are actually doing different hand of people actually doing different things that where you cause a lot of issue. This is the thing, you need to have communication, you need to have a teamwork over there. So that's how things being solved, and you need to understand how it is actually being solved, being explained, and get to know the root precisely. So nothing else that I actually wish to explain more. But on top of that, my next video, I really hope that I would actually explain about a basic timing analysis. Actually, the thing is that a lot of people actually always sees timing report. They always see timing report. Hey, I'm gonna fix it, set up, so I have to make sure my data is actually move faster than your clock. And then when it comes to whole, I want to make sure my data is actually coming later after your clock being actually arrived. So whenever you have this kind of mentality and you are reading your timing report without knowing how is the formula, how is the terminology. And on one point, I think it's important to really know the terminology whenever you actually do certain things. That's how you get connected to that particular area. So here it is. I actually called it a day by saying few things here. Is that one thing here it is that we might actually know a lot of knowledge. We might actually know a lot of things, but the moment you actually know how to do the connection between dots, that's where your intelligence kicks in. You really need to know how it is being interrelated into 2 parts or 3 parts. Then only your intelligence will kick in and you able to actually solve it seamlessly. I think that's all about my sharing today. And if you guys really like it about the sharing, and if you really feel that there are few things I'm able to actually understand, drop it a comment and I'll definitely reply to it. Thank you so much and have a good day.